Elliptic curve digital signature algorithm. In cryptography, the elliptic curve digital signature algorithm, ECDSA, offers a variant of the digital signature algorithm, DSA, which uses elliptic curve cryptography. Key and signature size. As with elliptic curve cryptography in general, the bit size of the public key believed to be needed for ECDSA is about twice the size of the security level, in bits. For example, at a security level of 80 bits, meaning an attacker requires a maximum of about 280, \displaystyle 2 to the power of 80, operations to find the private key, the size of an ECDSA private key would be 160 bits, whereas the size of a DSA private key is at least 1024 bits. On the other hand, the signature size is the same for both DSA and ECDSA, approximately 4T, \displaystyle 4T, bits, where T, \displaystyle T, is the security level measured in bits, that is, about 320 bits for a security level of 80 bits. Signature generation algorithm. Suppose Alice wants to send a signed message to Bob. Initially, they must agree on the curve parameters, curve, G, N, \displaystyle, \textstring, curve, G, N. In addition to the field and equation of the curve, we need G, \displaystyle G, a base point of prime order on the curve, N, \displaystyle N, is the multiplicative order of the point G, \displaystyle G. The order N, \displaystyle N, of the base point G, \displaystyle G, must be prime. Indeed, we assume that every non-zero element of the ring Z, NZ, \displaystyle \math, Z, /n \math, Z, is invertible, so that Z, NZ, \displaystyle \math, Z, /n \math, Z, must be a field. It implies that N, \displaystyle N, must be prime, cf. B's outside identity. Alice creates a key pair, consisting of a private key integer dA, \displaystyle d sub a, randomly selected in the interval, \displaystyle, and a public key curve point q equals dA times g, \displaystyle q sub a equals d sub a times g. We use times, \displaystyle \times, to denote elliptic curve point multiplication by a scalar. For Alice to sign a message m, \displaystyle m, she follows these steps. As the standard notes, it is not only required for k, \displaystyle k, to be secret, but it is also crucial to select different k, \displaystyle k, for different signatures, otherwise the equation in step 6 can be solved for dA, \displaystyle d sub a, the private key, given two signatures, r, s, \displaystyle, r, s, and, r, s, \displaystyle, r, s, employing the same unknown k, \displaystyle k, for different known messages m, \displaystyle m, and m, \displaystyle m, an attacker can calculate z, \displaystyle z, and z, \displaystyle z, and since s minus s equals k minus 1, z minus z, \displaystyle ss apostrophe equals k to the power of minus 1 zz. All operations in this paragraph are done modulo n, \displaystyle n. The attacker can find k equals z minus zs minus s, \displaystyle k equals \frac, zzss. Since s equals k minus 1, z plus rda, \displaystyle s equals k to the power of minus 1 z plus rho sub a, the attacker can now calculate the private key dA equals sk minus zr, \displaystyle d sub a equals \frac, skzr. This implementation failure was used, for example, to extract the signing key used for the PlayStation 3 gaming console. Another way ECDSA signature may leak private keys is when k, \displaystyle k, is generated by a faulty random number generator. Such a failure in random number generation caused users of Android Bitcoin wallet to lose their funds in August 2013. To ensure that K is unique for each message, one may bypass random number generation completely and generate deterministic signatures by deriving K from both the message and the private key. Signature verification algorithm. For Bob to authenticate Alice's signature, he must have a copy of her public key curve point QA /Q sub A. Bob can verify QA /Q sub A is a valid curve point as follows. After that, Bob follows these steps. Note that an efficient implementation would compute inverse s-1 mod n /s to the power of -1 /mod /n only once. Also, using Shawmere's trick, a sum of two scalar multiplications u1 times g plus u2 times qa /u1 times g plus u2 times q sub a can be calculated faster than two scalar multiplications done independently. Correctness of the algorithm. It is not immediately obvious why verification even functions correctly. To see why, denoters see the curve point computed in step 5 of verification. From the definition of the public key as Q equals dA times G, /Q sub A equals D sub A / G. Because elliptic curve scalar multiplication distributes over addition. Expanding the definition of U1, /U1, and U2, /U2, from verification step 4. Collecting the common term s-1, /s to the power of -1, expanding the definition of s from signature step 6. Since the inverse of an inverse is the original element, and the product of an element's inverse and the element is the identity, we are left with. From the definition of R, this is verification step 6. This shows only that a correctly signed message will verify correctly. Many other properties are required for a secure signature algorithm. Public key recovery. Given a message M and Alice's signature R, S, /R, S, on that message, Bob can, potentially, recover Alice's public key. Note that an invalid signature, or a signature from a different message, will result in the recovery of an incorrect public key. The recovery algorithm can only be used to check validity of a signature if the signer's public key, or its hash, is known beforehand. Correctness of the recovery algorithm. Start with the definition of QA, /Q sub A, from recovery step 6. From the definition R equals, x1, y1, equals k times g, /R equals x sub 1, y sub 1 equals k times g, from signing step 4. Because elliptic curve scalar multiplication distributes over addition. Expanding the definition of U1, /U1, and U2, /U2, from recovery step 5. Expanding the definition of S from signature step 6. Since the product of an element's inverse and the element is the identity, we are left with. The first and second terms cancel each other out. From the definition of Q equals dA times G, /Q sub A equals D sub A / G, this is Alice's public key. This shows that a correctly signed message will recover the correct public key, provided additional information was shared to uniquely calculate curve point R equals x1, y1, /R equals x sub 1, y sub 1, from signature value R. Security. In December 2010, a group calling itself Failzero Overflow announced recovery of the ECDSA private key used by Sony to sign software for the PlayStation 3 game console. However, this attack only worked because Sony did not properly implement the algorithm, because K, /K, was static instead of random. As pointed out in the signature generation algorithm section above, this makes DA_D sub A solvable, rendering the entire algorithm useless. On March 29, 2011, two researchers published an IAC paper demonstrating that it is possible to retrieve at less private key of a server using OpenSSL that authenticates with elliptic curves DSA over a binary field via a timing attack. The vulnerability was fixed in OpenSSL 1.0.0e. In August 2013, it was revealed that bugs in some implementations of the Java class secure random sometimes generated collisions in the K value. This allowed hackers to recover private keys, giving them the same control over Bitcoin transactions as legitimate keys owners had, using the same exploit that was used to reveal the PS3 signing key on some Android app implementations, which use Java and rely on ECDSA to authenticate transactions. This issue can be prevented by an unpredictable generation of K, \K, for example, a deterministic procedure as described by RFC 6979. Concerns. There exist two sorts of concerns with ECDSA. Both of those concerns are summarized in libscurve 25519 Introduction. Implementations. Below is a list of cryptographic libraries that provide support for ECDSA. Example usage. Wikipedia.org uses ECDSA in Atlas Cipher Suite to authenticate itself to web browsers, which the following abbreviated transcript shows.